who will talk about non-blow-up mechanisms in the Landau-Coulomb equation.
Hi, everybody. First, thank you to Jacob and Jinwei for asking me to give a talk to this workshop. So today I will present, if I have time, two works, and they all concern blow-up and non-blow-up mechanism for the Landau-Coulomb equation. So first I will concentrate on the homogeneous version. So this is the standard form, so the function f is the particle density, is a positive function in two variables, the velocity and the time, and obey a parabolic equation, second order, anisotropic. So the diffusion is anisotropic and has a quadratic nonlinearity. So the Landau collision operator, the original form, and it's written in an integral form. So we have the divergence in V, and then the integral of this binary term. And if we do some manipulation inside this integral, and we combine it with the divergence, we arrive at this somehow more compact form. And you see why I said this is a quadratic nonlinearity. So this f square appears on the right-hand side. It's second order, and the diffusion coefficient is anisotropic. So the capital A is a matrix, and is the average of f with a kernel. This kernel comes from the Coulomb interaction, but there is a projection matrix in front. The projection matrix identity minus. I mean, this is the standard projection matrix. So you can imagine that there will be some directions along which the diffusion is very small, and other directions along which this term here is basically like a Laplacian, more or less. Okay, the diffusion is, of course, depends on f. Okay, so not really a Laplacian, but something that is fully uniformly elliptic. Okay, so the uniform ellipticity in some sense decays for large velocity. So the conservation of mass first and second momentum imply that this coefficient, the diffusion coefficient capital A, is bounded by a constant. This constant here depends exactly on the mass first and second momentum and entropy of the initial data over 1 over v cube. So we have somehow a uniform ellipticity, but loses power for large velocity. So what do we know about this equation? Well, assume that the initial data are sufficiently regular, and I'm not specifying what it means, but so for example, mass, all the physical quantities are conserved, the entropy is bounded, and maybe some moments. Okay, then we have local in time existence and uniqueness of smooth solutions. So as soon as we start, there is a smooth solution. There are smooth solutions. Actually, there is one, because there is also uniqueness. But this result is only local in time. If the initial data are very small in some Sobolev norm, for example, in the Maxwellian, then we have global in time solution. But for general initial data, not small, not close to Maxwellian, the global in time existence seems a little bit more complicated, and basically the problem is open. Okay, and the term f square, this quadratic nonlinearity here, of course, suggests that maybe blow up might be possible, right? We don't know if that exists or not, but it might be possible. So the main question is if the standard conservation law are enough to trap the solution in a compact set. Okay, so the analysis and some manipulation suggest that blow up might occur if one can keep most of the mass in a small ball. Okay, in fact, The contrary is true, that if the integral of f in a small ball is small when r goes to 0, then we have global well-posedness. Okay. So then, so the main question is, can one construct such blow-up singular solutions, or can one rule them out? Okay. And so today I will present, I think we were surprised that this analysis was not done yet, but so I will present how to eliminate existence of actually one particular breakdown mechanism. There may be many of them, but today I will focus on one, which is the one called approximately self-similar blow-up. So what this means is that we take our function and we write it as the sum of two terms. The second one, calligraph E, is an arrow term. And the first one is somehow the self-similar term. And this coefficient lambda and mu they approach 0 when small t approaches capital T. And so they are positive, and the arrow term, calligraph E, is less singular than 1 over mu. Okay. So if you think this way, that we concentrate of type 1 blow-up profiles. So this means that the blow-up rate 1 over mu is given, as I'll show you in the next slides, by the rescaling symmetry of the equation. Okay, so this is, as I said, one particular breakdown mechanism. There can be many others that we don't know. They might not exist at all, or they might exist. And so the Landau equation, in fact, has a very rich scaling symmetry, similar to fluid equations. So it's very different from semilinear heat equation, where the scaling symmetry is one parameter. Okay. So the Landau equation, as the Boltzmann equation, has two parameter scaling. So if f is a solution, so is f of lambda alpha defined in this way for any lambda and for any alpha. So if one looks for a breakdown mechanism and for analyzing how this can go, this is a very rich kind of problem. So, and the same is for, so this is the homogeneous, and very similar is for inhomogeneous. So we have a two parameter scaling as in fluid equations. So so this is the main theorem. So this is in collaboration with Jacob and Stan Snelson. So let's consider the Landau equation. So smooth solutions actually of the Landau equation written in this form. So if f is smooth, both formulations, and I showed you earlier, and actually others, are all equivalent. Okay. So we start with this one. And we assume then f, our solution f, is smooth and has a finite mass and second moment bounded, and is C infinity up to a certain time, capital T. So if f has this form, so it's a function phi plus 1 over t minus capital T, and the self-similar part, and where this theta is a parameter between 1/3 and 1/2, then if the solution has this form, then we must have G equal to 0. Okay. So the term that blows up at a rate 1 over t actually has to be, doesn't exist. Okay. So let me let me comment couple of comments on this ansatz. So again, we have a two parameter scaling. So this theta here represents, is actually 1 over alpha in the previous slides. Okay. And why do we choose this range of theta? Well, this comes from some consideration. So for example, when theta is less than 1/3, then this would not satisfy the L1 condition. Okay, so it means that the function will blow up in L1, and this is not physical. Okay, and when theta is greater than 1/2, then we would have a bound in a high LP norm, and this is also not reasonable to assume, because we know that if your function f is bounded in some LP norm with p high, then we don't have blow up. Okay, so I will show this very clearly in the next slides. But so the answer is that, so we take a f and then we decouple in two parts. The first part, so this G is the blow up singular solution, okay? And then we have a less singular part. So at the time capital T, the contribution of phi is actually small. So we don't say that this phi doesn't blow up, but can actually become unbounded at a subcritical case. Okay. Can be. And okay, so here is the is some comment on the parameter theta. So why does it make sense to consider theta less than 1/3? In principle, theta can be what you want, right? It's a 2-parameter scaling, okay? But it doesn't make any sense to consider any parameter theta less than 1/3 because we violate the conservation of mass, which is I mean, given, right, for homogeneous. Okay. Now, if theta is greater than 1/2, on the other hand, some LP norm with p greater than 3/2 are bounded, or d/2 in d dimensions are bounded. And if we know if this is true, then we have global closeness. Okay, so we have to blow up in some norm greater than 3/2, and this happens in this range of parameters. So again, possible blow up might include other profiles. Okay, so this is one particular given by the self-similarity scaling. There can be others. And in particular, there can be others which blow up at a faster rate. Okay. Type 2, for example. But those are where, at least when we were working on it, very hard to detect. And the analysis became a little bit complicated, and maybe we weren't too consequent. I don't know. So, but I mean, those are much harder to detect. So the same result as I showed in the previous theorem holds for the inhomogeneous Landau and inhomogeneous Boltzmann and the Vlasov-Poisson Landau equation, the equation that Alexander Bobilev just talked about this morning. So in particular, we have, and actually not only for Coulomb, but for all range of very soft potentials. So if we consider the inhomogeneous Landau equation, now we have the spatial variable, and then in particular, so we consider all the potentials from Coulomb to -2, or in d dimension, actually between -d and -2. So as before, if we write make the answers that the function f is can be written as like a subcritical term, and the self-similar variable with the rescaling that is given by the equation, then if theta is between -1 and 1/2, then we must have g equal to 0. So this part here does not exist. And here you see the range of parameters have slightly changed. The theta greater than -1, you can see why we put it, because we are interested in blow up that happens at a specific point. Okay, so we are not looking at infinity. Okay, so theta, we consider theta greater than -1, and theta less than 1/2. So the previous, the justification that I gave you for the homogeneous, now it becomes a little bit more somehow foggy, because there is not, there isn't a strict theory that says that if you are in some LP uniformly in time and maybe in space. There is, but in L infinity, right? So, or anyway, so, but here the 1/2 comes from the analysis, but I think it comes, is needed because the the power 2, right, is the order, is the power of the is the order of the parabolicity, okay, of the diffusion here. And for Boltzmann, we have exactly the same. So it's a little bit repetitive, I know, but the scaling is the same as in a homogeneous Landau. So the same ansatz holds for Boltzmann, non-cut off, any gamma between -3 and 1, and S between 0 and 1. So if the function f has this form, then at this one is greater than 0, obviously, then we must have that this part is identically 0. And the 1/2s, the range of parameter, comes from the fact that the Boltzmann operator has order 2s, not 2, s less than 1. Right? So it's a parabolic equation of order 2s. Okay. For us, it comes from to control some terms in our asymptotic matching, but I think it really reflects the fact that the order of the diffusion of the higher order operator is 2s. Okay, so let me sketch the proof for the homogeneous. Somehow this is simpler and less terms. The procedure is exactly the same. So we take our solution, right? We plug it in, and then we match all the terms. So if in the first row you have the terms of order 0. Then the second one of 1 minus 2 theta, and then 1 plus 2 theta. And remember, we are in the homogeneous Landau, so both this and this are positive. So the to show that the only solution of this equation is g equal to 0, well, we will show that the error terms will disappear when little t approaches t, and then the only solution of the leading order term, the leading order equation, is just the identically 0 solution. This is exactly what happens. So if we call it calligraph 1, calligraph E1 sub 1, this the second row, and calligraph E sub 2, the third row, then by assuming some regularity and some decay at infinity of the phi and some regularity of the g. Now this formulation here is written in the self-similar variables. So for example, the Hessian of g in self-similar variable is very smooth and everything else. So we can show that the two terms in the L infinity norm disappear when the time t approximate and approaches the blow-up time, let's say, capital T. Okay, so those two terms disappear, and then if one concentrates on the leading order equation, then by simple, actually the integrating, for example, the whole equation in dW, one can see if theta is not 1/3, the only solution is 0. If theta is 1/3, sorry, this should be equal 1/3. So if theta is 1/3, I cannot do simple integration. We first multiply by the W square, integrate, and we get this expression. And since G is greater than 0, the only possibility is, again, that G is to be identically 0. Okay. So the proofs of saying that some profiles do not apply is actually much easier to say than some self-similar blow-up actually is stable, or as it happens in Seeger semi-linear heat equation. To show that some blow-up profiles actually are admissible is much harder. than to rule them out. To rule them out is just some simple asymptotic matching terms and try to show that they disappear, right? And this is fortunately what is happening here. And the same similar structure of proof is applies for inhomogeneous Landau, inhomogeneous Boltzmann, and the Vlasov-Poisson-Landau equation, the equation that we have seen in Bobilev talk. Interestingly, as soon as we couple Landau with Poisson, the system becomes a one-parameter scaling. Very interesting. So the coupling somehow kills the second parameter. And we are back to a one-parameter scaling. But as for the analysis and for the ruling out of this blow-up profile, the things is, it makes no difference. Okay, the difference will be when one wants to rule out faster decay rate, faster blow-up rates, because there the things are much harder to analyze. So to have a two-parameter scaling is very complicated. Okay, so then some remarks. So we rule out one particular mechanism of blow-up. So if, however, say if some other mechanism of blow-up occur, then this one is transient. So this is called transient, meaning that solution after the blow-up time will become bounded again. And this was proven very recently by De Villet, he and Zhang in 2021. The paper appeared last year. And they showed that there exists a time, capital T naught, that only depends on the entropy and on the H1 norm of the initial data, such that after such time T naught, any solution, no matter what happens before, becomes again bounded, okay, and live forever. So if there is blow up in the homogeneous Landau, this is transient. It doesn't happen after a time that actually can be explicitly computed, and it does not happen for infinite time. Okay. And the second result that I wanted to present today was something somehow related to this, to the transient behavior of the blow up for homogeneous Landau. So the result that it was is in collaboration with François Golse and Cyril Imbert and Alexis Vasseur regarding the partial regularity. Okay, partial regularity result for the homogeneous Landau. So that is the following. So if we're given a solution, so let me define now what is a singular and what is a regular time, and then we go on the theorem. So let's assume that we have f is a function and a time t. Okay, so the time t naught is called regular for f if there exists an epsilon such that f remains bounded in the time interval t naught minus epsilon t naught. So this time, if something like this exists, then T naught is called a regular time. T naught is called a singular time if it is not regular. Okay, so if there isn't any interval before T naught where my function is bounded. So the partial regularity results said that if we take all the singular times of the solution to the homogeneous Landau equation, for sufficiently regular initial data, and for us, regular means we need some high moment, but not in any Sobolev space, I believe. So we need the entropy bounded, but not small, not nothing out of the ordinary. Then the Hausdorff dimension of the set of all singular times is at most 1/2. Okay, it's not larger than 1/2. This is exactly this result is exactly in line with the transient characteristic of the blow up. So it cannot be dragged forever somehow. So the proof of this theorem uses, as you can imagine, the Giorgi method, uses a parabolic version of the Giorgi method, but with some modification. So it is a problem that, I mean, somehow something that we always get stuck in, to know that for Landau we cannot do any LP estimate unless P is 1. Okay, so the Giorgi would be the classical De Giorgi used to say, well, that if you are LP for some P, then in a ball, then you are an infinity in a smaller ball somehow, right, morally. But for us, this LP is not available. So the LP is replaced by the entropy, which is somehow the only Diliakonov function that is not to exist for Landau. Okay, and replaced by the entropy. So the step, so the gaining regularity goes actually between, then the entropy is bounded to L infinity in a smaller set. And so the classical level set that we use, that is used in the Giorgi iteration process, is replaced by a truncated entropy. Okay, so the entropy is the F log F, right, the standard one. But now we truncate that, and we take our function F. We consider the set where F is greater than a certain constant CK, and then we consider this functional. And this is what the starting of our level set approach a la De Giorgi somehow. And I know this, so then you might say, okay, but this one, what are the properties of this? It's a truncated entropy, but it might not decay. Yes, this is, that's why we get partial regularity, right? And not full regularity. At some point, we cannot rule out that there are no singular sets. Okay, but let me tell you what we do and what is available by using this functional. But one thing I want to remark is that the use of the entropy F log F in the De Giorgi settings, like truncating this functional and then looking for the iteration process, was introduced by, at least it's the first time then I saw it, by Thierry Goudon and Alexis Vasseur in 2010 for a system of reaction diffusion equations. Okay. But I think in this system they could get full regularity. Right? So the proposition. So the main theorem is actually based on two main propositions, and then at the end one covering argument. So the two propositions are the same. So assume that in a cube or in a ball, and when I mean a ball, I mean a space and time and velocity. Okay, so assume that in a certain ball, the entropy, the cutoff entropy, and we cut the F at 1/2. Say all those constants can be changed, but let me fix them for now. So if we take F and you cut off the F, so you consider only where F is greater than 1/2, and you compute the corresponding entropy. So if this integral is less than a certain constant eta naught, okay, and this 1/8 over n1 is the time interval, okay, then what's happening is that the F will be bounded by another constant, 2 in this case, in a smaller time set, 1/2, 1. So we started with 1/8 and 1, right? The whole space. And there the entropy, the entropy is bounded. And then we can show that we are actually bounded by a constant 2 in a smaller time interval, 1/2, 1. All those constants are now just fixed for simplicity of the computation. And okay, so then once we have this one, somehow we have to go back to the original problem, right? So we need some rescaling. So then we have an improved bound on the entropy, and we say that if gradient of f to the 1 over q minus a constant to the power q, so this will be somehow we cut off the function at a certain power epsilon, and we take the gradient in LQ somehow morally, okay? And if this integral is small, when epsilon is small, then my function f is bounded by a constant then depend on epsilon for almost every t in 1 minus delta n 1, okay? And after that, the Hausdorff dimension, less than 1/2, comes from a Vitali covering argument. So we are taking all the times in which this is not satisfied, and by covering that and doing some I mean, there will be a countable covering of the interval, and then we can get then the singular times. The set of the singular time has Hausdorff measure and most 1/2. So this result is very similar to what we know about Navier-Stokes. So basically, if you want to make the parallel to what we know about Navier-Stokes and the numerology, so if f is the solution of the Landau equation, the square root of f will be the u in Navier-Stokes somehow. This is the parallel, and at least in this aspect. Okay. So I still have a couple of minutes, right? So then let me show you at the now about this cutoff entropy. So if we take the time evolution of the entropy cutoff at a certain constant ck, then we will have then the time derivative plus a certain, this is somehow the Fisher information, integrating the domain where f is greater than ck, is bounded by the L1 norm. This is a very interesting term. So this is going to be the L1 norm of the cutoff function times 1 plus ck. And somehow, if you remember the term that was in the Landau, the f square, this is a singularity which is less than a depleted singularity. We don't really get the f square or the square of the cutoff of the level set, but something which is of lower order. Okay, so this is good. So what do we do with this with the Fisher information? And it's not completely the Fisher information, but it's weighted. So to remember, this was the 1 plus v cube was the bound below of this diffusion matrix. Then I showed you at the very beginning. So every time that we do LP or whatever estimate, and we use the diffusion coefficient, there will always be this weight. This is inevitable. But we can get rid of this by adding some momentum of f. So if actually this term over here times some constants, then depends on high enough moment of f, bound from above the integral of somehow a let's say L, so the gradient of f to the 1 q minus the constant to the 1 over q, and q is any power between 1 and 2, not 2. Unfortunately, we cannot get 2, but something slightly less than 2. Okay. So somehow you see now, if you are familiar with the Georgi method, how it works is that, okay, so we do our estimate, and then at some point we need to get an estimate on the gradient, and then from the estimate on the gradient we need to get some LP norm, right, bounded by the gradient and the soup of some LP. So now we have the entropy. So we already got the bound on the gradient. So if you think about the heat equation, that this could be the gradient of F, the L2 norm space-time of F, of the gradient of F. But here we get something less, because we have to deal, first we start with the Fisher, right? And then we have to deal with the moments. That's fine. But now we have to somehow show that the entropy bounds some LP norms, right? Otherwise, I cannot put together the Georgi iteration process, because I need some LP norm, so then the gradient, and then so equal then the LP norm at the previous level set to some power greater than 1. Okay, so we need to build that. And well, the entropy F log F is bounds the minimum somehow between the L1 and the L2 norm. Okay, near 0 will be the L2 norm, and then when F is big will be the L1 norm. Okay, so then this is the left-hand side. Okay, and so then now we have after this one, then we will build the Georgi recurrence relation involved with the mu k. So I have everything now. I have the mu k, which is this one here, and we have the gradient of the mu k, which is exactly this one. And so this is the term that will be the starting point of the recurrence. Okay, so now the goal is to show that the capital AK will be less or equal than a constant times a k minus 1 to a power bigger than 1, right? And if initially the A naught is small, then the limit of AK when gate goes to infinity will give me exactly 0, and will tell you that the F is below a certain constant. So let me show you more sorry, did I say here? Okay, so then exactly, this is, I was looking for those. So now, after I build basically all the blocks for the Georgi, we need to define what is the CK and what is the time interval. You remember at the beginning I said 1/8, 1, and then we prove L infinity is 1/2, 1. So now somehow I need to set up those parameters. So I take a sequence of times where a t at 0 will be 1/8, and it goes up to 1/2. And then I take a sequence of cutoffs, CK, then starts, I don't know, at 1 and grows to 2. Okay. So then I defined the A sub k this way. So here you see that the time goes between T sub k and 1. Okay. And so by doing iteration, basically it's just a circle that goes on and on. One can show that A sub k is less or equal than a constant to the power k times A k minus 1 to a certain power beta. And beta is exactly this quantity here, 8/3 minus 2q. And to close my argument, I need beta greater than 1. This will restrict, so then this means that we can consider Q anywhere between 6/5 and 2. I had no restriction, sorry, I had no restriction on Q before. The inequality that I showed you before was true for any Q between 1 and 2. So, okay, so this means that my Q here, any Q greater than 6/5 is great for me. Okay, that's fine. So then if the A naught is small, and the A naught is exactly this term over here, you recognize this from the main theorem, So this inequality here implies that as k goes to infinity, ak goes to 0. So which means that the f will be less or equal than 2 in the time interval 1/2 1, almost everywhere in velocity. So here we consider smooth solutions. So, well, actually not so smooth, but solutions then can be defined almost everywhere in the space. So then f is less than 2. Okay. So then what do we do? Okay, so now we need to go back to the original equation and get all the theta naught 2 somehow straight up a little bit. So what we do is that we rescale the function f. So if we have a solution of the Landau equation, then we rescale it in this way. And do you remember, this is exactly the rescaling that is conserved by the equation. We saw that at the very beginning, right? So now my parameter will be 2 to the power n, and this gamma here. This gamma here, I pick it in a certain way, okay? So, and then what we do is that, well, we say if I have my f and I rescale it in this way, I can find a big N such that at some point after a certain threshold, the entropy cut at 1/2 for Fn is smaller than the constant that I had in the previous proposition. Okay, I'm not saying that this happens for any function f, but I rescale it, and then if thanks to this rescaling, I can find an n big enough so that this quantity here is less than eta naught. Okay, and if this quantity here is less than eta naught, it means that f sub n is less than 2. Okay, this is the proposition we just saw. If f sub n is less than 2, then f is less than a constant, which is big. Okay, that's fine, it's big, but that doesn't matter to us. In a time which is between 1 minus, sorry, this is, there is a negative sign here, 1 minus 1 over 2 to the n naught and 1, okay? And so this is true, okay, so in this time interval. So if now we consider all times that this is not true, then a Vitalik covering argument says that if we take the Hausdorff measure of all the singular times, this has to be less than 1/2. Okay, and I think with this I will conclude. Thank you.
Great, yeah, thanks for that talk. Are there any questions for Marie? Okay, well, I guess I can ask the really obvious one. No one else will. So I guess in trying to adapt something like Caffarelli-Cohn-Nuremberg, is it just that it's super hard and you haven't finished it yet, or you think that there's something really fundamental?
Well, Cyril, where is Cyril? I don't remember. We were talking with him just yesterday. It seems it's very hard to do the Caffarelli-Cohn-Nuremberg for Landau. At least this is what I was told. But I think this is what is happening, yes, because we have very little regularity to make the estimate close somehow.
Yeah, but do you think it's like hard in the sense of you'll have a paper in like a year, or like hard in the sense of
interesting.
No
This is
That's
I don't know.
I see.
I don't know.
Okay.
Yes, actually, the timing it depends on the people working on it.
That's true. That's true.
But I don't know yet. Yeah, I have no idea.
Okay, I know. I was just curious.
Yeah. I mean, this is exactly the next natural step.
Yeah.
After proving that you have a small set of singular times, then the next is to show that the surface is.
This is much harder than the proof for Navier-Stokes. So this.
I know. It's
already a
yes,
flag.
yes, absolutely, yeah. Yes, and so hopefully the proof for Landau of the lower dimensional maybe not as hard as Navier-Stokes, but I don't know, maybe.
I don't know.
There was another, sorry, I'm the moderator, but there was another question down there. Okay.
Yeah.
Yes, so when I say blow up, it's in L infinity. Yes, so I think so. Theory says that if for homogeneous, okay, so if the solution becomes unbounded in L infinity, becomes unbounded in any norms up to d/2. Okay, so it's basically equivalent to consider blow up in L infinity or to consider blow up in a LP norm uniformly in time. Moments, I think the moments is, so for the moments, I don't know. So for example, when you consider the symmetric case, and then say you have a blow up at a point, maybe it's equivalent somehow to consider blow up in moments, and I cannot.
For the homogeneous problem, don't you, for self-similar singularities, don't you need it to be positive so the moments won't blow up?
They won't blow up.
Yeah.
Is that so? For this blow up, then we said the moments do not blow up. For the homogeneous case, at least the second one, but we don't know the also the higher one. That one I don't remember. Yeah.
Yeah, it depends what G is. So it's a little unclear, but it has to blow up in L infinity, and maybe the other ones blow up too. But for the inhomogeneous case, you get all kinds of.
So my idea is that for homogeneous there isn't much of a difference.
Are there any other questions?
No.
Oh. Okay. Okay, so if there's no other questions, let's thank the speaker again and let's break for lunch.
Thank you. Thank you. Sorry.